let's jump right into this explainer, because today we're investigating a truly wild cosmic mystery. Exactly where do the heaviest elements in our universe actually come from? We're going to explore some of the most extreme, violent environments in the cosmos to track down the origins of the materials that literally shape our world. Seriously, take a second to look at a gold ring, or maybe think about the platinum hidden away inside the phone or computer you're using right now. Ask yourself, where were these precious metals actually forged? Because for a long time, the answer really wasn't entirely clear. I mean, we knew they weren't made here on Earth, but the exact cosmic forge, that remained a massive puzzle. And the heart of our mystery is brilliantly illustrated right here. You see, while lighter elements are born in the Big Bang or inside standard living stars through fusion, human synthesis and standard stellar fusion simply cannot account for the vast majority of heavy elements. Stuff like gold, platinum, or uranium. Normal stars just don't have the extreme conditions required to build them. So, to solve this puzzle, we first need to quickly talk about nucleosynthesis. Put simply, this is the underlying mechanism for how the universe builds heavier elements from pre-existing building blocks, protons and neutrons. Since atomic nuclei are positively charged, they naturally repel each other. To build really heavy elements, you have to somehow bypass that repulsion. And the universe does this by bombarding seed nuclei with neutrons, which conveniently have zero charge. Now, there are two main nucleosynthesis methods for heavy elements. First up is the S process, or slow process, which happens in giant, aging stars. It's kind of like slowly eating a meal. A nucleus captures one neutron, takes its sweet time to digest it through a radioactive process called beta decay, and stabilizes before taking another bite. But our focus today, the R process, the Rapid Neutron Capture Process. And this is not a slow meal. This is literally like drinking from a fire hose of neutrons. A seed nucleus captures dozens of neutrons instantly, way faster than it can possibly digest them. When you actually look at the numbers, the difference is just staggering. The S process takes decades, sometimes up to 100 years to capture a neutron in a modern environment. The R process, we're talking microseconds to milliseconds, requiring mind-bending, astronomical densities. Because of this, the S process completely tops out at bismuth, but the R process is uniquely responsible for creating the absolute heaviest elements in existence, like thorium and uranium. Charting out this creation path reveals a really stark contrast. While the S process closely hugs the safe valley of stable elements we're familiar with, the aggressive R process violently pushes nuclei far, far away from stability. It runs right along what physicists call the neutron drip line. This is the absolute physical limit where a nucleus is so stuffed, it literally cannot hold even one more neutron without it dripping right off. Of course, these swollen, incredibly unstable nuclei can't stay on that drip line forever. Once that neutron fire hose finally shuts off, they must undergo beta decay. They rapidly emit electrons, converting their excess neutrons into protons, and cascade back down toward that valley of stability. Along the way, they hit certain structural waiting points at magic neutron numbers. And that's absolutely crucial, because those waiting points ultimately dictate the distinct abundance peaks of the heavy elements we mine right here on Earth today. But let's just pause on the sheer physics required to actually make this happen. To make the R process work, you need 10 to the 24th power free neutrons per cubic centimeter. Just to visualize that, that is almost an entire gram of pure free neutrons packed into a space the size of a single sugar cube. I mean, these are absolutely not conditions you find in a normal star. Section 1. The prime suspects hunting extreme environments. So, knowing the massive physics required, the huge question became, what cosmic environments could possibly provide such violent conditions? Well, our prime suspects are the most catastrophic events in the cosmos. We're looking at core collapse supernovae, highly magnetized spinning supernovae, epic collisions between two incredibly dense neutron stars, and collapsers, which are massive stars collapsing directly into black holes. For decades, the leading theory was actually the core collapse supernova. When a massive star runs out of fuel, its core collapses under its own gravity and then rebounds in a spectacular explosion. Scientists firmly believed these explosive deaths were the primary crime scenes for the R process, assuming they provided that rapid burst of neutrons we need. But as supercomputers allowed us to run more complex simulations, the supernova theory hit a major roadblock. Basically, they had an alibi. Advanced models showed that the intense neutrino fluxes emitted from the newly formed proto-neutron star during a supernova actually interfere with the whole thing. The neutrinos equalize the number of protons and neutrons, which essentially starves the environment of that massive neutron excess required to reach the heaviest elements like uranium. Supernova might produce the lighter R process elements, sure, but they really struggle to explain the heavy ones. Section 2. The Smoking Gun, GWV 17017. For years, this theoretical debate just raged on. But then, on August 17, 2017, humanity finally found the definitive smoking gun. At time zero, the LIGO and Virgo observatories detected ripples in the fabric of space-time, gravitational waves from a binary neutron star merger. Within hours, telescopes all over the world pivoted to pinpoint the exact location. And over the following days, they captured the optical and infrared aftermath of the collision, a spectacularly glowing event known as a kilonova. This single event ushered in a totally new era of astrophysics. The light emitted from this kilonova wasn't just standard starlight, no, it was actually powered by the radioactive decay of freshly forged heavy nuclei. The spectroscopic data from this one event gave us our very first direct, undeniable visual evidence of the R process happening in real time. We literally watched the universe synthesize heavy metals. When scientists broke down the light spectrum, the kilonova revealed two distinct clouds of ejected material. First, you had these hot blue masses expanding rapidly, which pointed to the creation of lower mass R process elements. But more importantly, there were cooler red masses. That red glow, that was the distinct signature of higher mass R process nuclei, the heavy actinides like thorium and uranium. It was total, absolute confirmation. Now, just to give you a true sense of scale for what we witnessed here, scientists estimate that this single, fleeting neutron star collision generated up to 13 Earth masses of solid gold. Just wrap your head around that for a second. Up to 13 times the entire mass of our planet, purely in gold, blasted out into space from just one collision. It's almost unbelievable. Section 3. An unfinished cosmic puzzle. So, while we did catch neutron stars completely red-handed back in 2017, this grand cosmic investigation isn't entirely closed just yet. We've still got some massive unanswered questions, like, are neutron star mergers the absolute only site for the R process? Or do other exotic events, like collapsars, pitch in? Astronomers are also trying to figure out if supernova play a backup role by fueling a weak R process that only makes lighter, heavy elements. And perhaps the biggest head-scratcher? Neutron stars take a really, really long time to form and merge. So, how exactly did the very earliest, oldest galaxies in the universe get enriched with R process elements way before neutron star mergers even had time to happen? To solve that timing issue, astronomers are diving deep into galactic chemical evolution. By studying ancient metal-poor stars out in the halo of our Milky Way, they can basically trace back the chemical history of the galaxy. These old stars show early signatures of the R process, proving that whatever site is responsible, it began seeding the interstellar medium with heavy elements super early in galactic history. And tweaking the models that track these stellar abundances over billions of years is exactly how we're eventually going to answer those lingering questions. So as we wrap up this explainer, I want to leave you with this final, honestly mind-blowing thought. When you look at the jewelry you wear, the electronics you use, or the very elements making up the core of our planet, is it possible that every single atom of gold on Earth is the direct result of two dead, hyperdense stars violently colliding in the dark void of space billions of years before our solar system even existed? The evidence absolutely points to yes, and that is simply incredible.